So in the last class, I showed you how you can convert the string matching problem into a Eulerian path problem. The problem essentially is that you're given an integer k and a collection of patterned k-mers, and the output should be the text, which essentially is the k-mer composition equal to the patterns. So in order to solve this problem computationally, the algorithm is you have to form a De Bruijn graph G out of the patterns. You add edges, you add an edge to make a modified graph, G prime, which is essentially a Eulerian, which satisfy the Eulerian conditions of being strongly connected and have in degrees equal to out degrees, which are even. And then you find a Eulerian cycle, and then you infer the Eulerian path in the graph G, given that you had two unbalanced nodes with odd in degrees and out degrees, and you convert this Eulerian path into the genome path, and that becomes, by following the path, you can basically give the text. So here, um, so basically, so far we have this was the outline, and that this is what I've covered in this particular module. There is something called assembling of read pairs, which you can follow in the textbook. This is an advanced part, so I'm not going to ask questions about it, but it follows exactly the same ideas as I've introduced you on single k-mers. The idea there is that instead of having a single k-mer or a single read, you basically have read that can be read from two parts. So for example, let us say newspapers was the DNA fragment that was being sequenced. So you will get information about the last three mer of the word newspaper. So you would essentially get new and ERS as your read. And when you talk about assembling read pairs, this is what this part of the book talks about. If you're interested, you can please feel free to go through that. And obviously, by having more information or more k-mer information, the depth of sequencing becomes better. You cover more genome, and therefore the problem of repeats goes away. So today I'm going to talk about some how so far the things that I've talked to you about is in the context of assuming certain things about how the DNA sequencing will happen. But there are these assumptions are not holding true always, and I'm going to talk about how to actually deal with these things when the assumptions are not holding true. Before that, I'll quickly discuss how do you find the Eulerian path. I think Vishantan asked last time. I put this video on Fleury's algorithm, and there's also another algorithm called higher Holzer algorithm, which basically are two ways in which you can again find Eulerian path. This is again advanced. I'm not going to ask you questions about that, but I'll quickly go through the algorithms themselves. So in the case of Fleury's algorithm, the main idea is you don't burn bridges. So bridges essentially is a edge. By if you disconnect that edge, then you create a disconnected graph. Okay. So for example, if you start from 2 and now you are having a choice of which path to take, you essentially take that path which is not a bridge path. So here, if you go take this path to the edge 1 2 or edge 2 0, these are not bridge paths, because if you remove these paths, then you are still able to reach the other node by the other edges. Okay, so this is the basic idea of Fleury's algorithm, and because you have to check whether a edge is a what's called it's a bridge edge or not. Therefore, the computational time that is typically associated with these kinds of algorithms is edge squared, because for each edge, you have to traverse all the other edges just to make sure that this edge is not a bridge edge. So that's what you do at each point of time when you are following the path. You don't take the bridge path. Okay. So when you are following following the Eulerian path here, you essentially take whenever you take that path, you essentially erase it from the graph. So for example, let's go from 2 to 0. So you erase that. Now from 0 to 1, there is only one path that you can take. So here you don't care about bridges, so you have to burn the bridge. So you take this path, then you take this one, and then you take this. So right. So this is the path that you'll have. So this is called the Fleury's algorithm. This is not very optimal, so because it takes a lot of time. The other algorithm is called the Heiss-Holzer algorithm. So here the idea is to insert unused cycles at each point of time. Okay, so let us say For doing this, you maintain two lists or two lists of nodes. One list of nodes is where you start from, and the other list of nodes is actually the circuit that you're talking about. So let us say that we start at the node 0. All right, we start to have the path 0, and this is a directed graph. So we go to edge 1. Okay, so we add edge 1 here, we remove it. Now at edge 1, we have a choice either to go to 3 or to go to 2. Let us say we go to 2. We are not checking whether this is a bridge edge or not, right? Because if it would be a bridge edge, then you will not be taking a 2, right? You will not burn this bridge. You will actually take this one, 3, and go ahead, right? Because if you remove 3, then you can actually go otherwise. So what you do is you take the 2, you take 2 and then you take 1, that this becomes your path, right? But the circuit you currently don't have. Now, since once you reach 0, there is nothing else that you can go for, right? So now what you do is you start to do back tracing. So you go back from 0 to 2, right? Then you go back from 2 to 1, right? And so because you are traversing this, now you're essentially you're going to be popping these things into your circuit. So essentially, whenever you are now going back, this becomes your circuit itself. So the first thing is that you will have 0, you have nothing, nowhere to go. Then the next thing is you go back, you have 2, this becomes a circuit. Now you go back to 1. Now when you are going back to 1, if that particular node has unused edges, any one of them is unused edges, then you again go through these unused edges in whatever direction you want. You basically complete the cycles, right? So this becomes a new cycle that you add. Now these edges get added into your current path, right? So 0 and 2 were popped out of your current path. And now essentially these 1 to 3, 3 to 4, 4 to 1 are going to be again added to your current path. Right now, when you are basically coming back to 1 and you have used all these edges, you'll start to pop these edges into the circuit. When I say pop, it is last in, first out, right? So for example, here first in was 0, last in was 2, right? So when you are essentially popping out things, you essentially pop out, so you start from 0. That's that's when you start to backtrace. Backtracing is first in, first out, but popping is last in, first out, right? So this is where you start from. So you add 0 and 2 here. So now when you have this circuit, you have these two things. Now you start to pop. So it's 0 and 2. Now you pop 1 here. You pop 4 here because it's last in, first out, right? So last in was 1, first out is 1, 4, 3, 1, and 0. And this becomes your circuit. Now, when you are actually traversing the circuit using this algorithm, it's again last in, first out. So it's 0, 1, 3, 4, 1, 2, 0. And you basically get the circuit. Now, because this is essentially, you don't care about whether a edge is a bridge edge or not. In this algorithm, the computational time is basically the number of nodes plus number of edges. So it's O of E plus vertexes V. All right. So this is just a brief example of how you would actually be finding these cycles. And once you find these cycles, then you can actually reconstruct the genome. Okay. So the complications that we had sort of assumed away when we were talking about genome assembly was that reads have perfect coverage. That essentially means that all the parts of the genome are going to be represented and all the k-mers from each part of the genome are going to be equally represented. The other assumption that we had was that sequencing machines are not error prone, so that the k-mer that you're getting is exactly what was represented in the genome. The other thing was that the exact multiplicities of the k-mers is known. So you already know that, okay, this particular k-mer is going to be occurring certain number of times because you are assuming that each k-mer is getting represented from the genome, and there is no some parts of the genome which have less k-mers being represented. And the other assumption is that the DNA is not double stranded, it's single stranded, but and may consist of multiple chromosomes. So yeah, so there might be disconnected graphs which would be coming, which would be representing different chromosomes. So these are the realities of genome assembly. And how do we actually deal with it? I'm going to talk about it now. So coverage is never perfect. Okay. So when we talk about coverage, it's almost like looking at television with different kinds of resolution. So the same image which you will be looking at in full HD is going to look much less sharper when you look at the same image at 8K resolution, right? So 8K resolution essentially means that the same part of the photo is being represented by more pixels. Okay. The same thing can be talked about genome assembly as well. If you are trying to piece together the original genome, if you are having more pieces to represent the same part of the genome, the picture that you're going to complete is going to be more complete, right? The picture of the genome that you're going to get is going to be more complete. So how does it translate to the real genome? So if you are looking at the genome like this, on the x-axis, it's the genome itself. So this is four different kinds of viruses. And on the y-axis is the depth, is the number of reads which are covering different positions of the genome. So you can see that when you actually do the sequencing, you create fragments of the genome and then you put them in the machine and you sequence and you figure out what was the actual letters in each of the reads. You see that this coverage is sort of unequal. Some parts are covered very highly and other parts are not covered as highly. All right. So this is a challenge. Now, this would essentially mean that there are some k-mers which are not found very often, and there are some parts of the genome which don't have k-mers at all being represented. Okay, so there are two concepts of coverage. First concept is
Why
coverage.
is this so?
Yeah.
So why is this so? Like, why do we have peaks here in these
So you
ones?
have peaks because this is like a so some parts of the genome are sometimes say modified, so it's not the same base, so the machine is not able to recognize, or it has causes errors. Other reasons is that those parts of the genome have, so because it's PCR dependent, right? So some parts of in PCR are more likely to be amplified otherwise than other parts. That's sometimes the case. But in most cases, it's the fact that the genome itself in those parts is not as accessible because it's bound by some proteins or things like that, which make the ability to sequence is not very is not uniform across all the parts of the genome because of this reason. Either it's modified or it's bound by a protein which uh, doesn't let you produce the fragments properly or protects against fragmentation, or you have some sort of technical biases in amplification of specific gamers or regions. Make sense?
Yes, sir.
Okay. So the other concept is coverage of reads themselves. So by when we say coverage of the reads, is the number of nucleotides in the reads, right, divided by the length of the underlying genome. So basically, when we talk about the genome coverage, we are typically talking about coverage of reads. You essentially say that, okay, this genome is having uh, a depth, a coverage depth of 20x. That means on an average, each nucleotide is overlapped by 20 reads, right? So that's basically number of reads multiplied by read length divided by the length of the underlying genome. Okay, so if you are supposed to write a pseudocode to calculate the coverage of the genome, how would you go about it? So the input here would be a set of DNA fragments with a constant length k, which are representing a genome, right? So if you want to calculate the coverage of the genome, first thing is that you have to construct the genome itself. You will do this by constructing a De Bruijn graph. So let's say you have this function called make De Bruijn graph. Input is DNA fragments, output is De Bruijn graph. Then you check whether this graph is balanced or not. It is Eulerian or not. So you check your input is whatever unbalanced graph. Your output is a balanced graph because De Bruijn graph, in this case of genome, linear genomes, this would be the case that the node which where the genome begins and the node where the genome ends, those fragments are not balanced. So you will basically balance them, and then you'll repeat until you have the graph strongly connected. You'll find a Eulerian cycle in this graph. After you found the Eulerian cycle, you can count the number of edges. So the length of the genome is going to be the number of edges, right? Uh, so it will be the number of edges plus it's a number of DNA fragments, which is equal to the number of edges plus k, which is the length of the your read itself minus one. So that's going to be the length of the genome, and the average coverage now is going to be the number of DNA fragments that were used initially to construct the De Bruijn graph, right? Multiplied by the length of the fragment, which is k, divided by the length of the genome. All right. I hope this is clear to everybody. this pseudocode.
Yes, sir.
I have rushed through this because I do not have time for this thing. All right. So how would you how would you deal with the cases where there is improper coverage of k-mers themselves? So what do I mean by improper coverage? So let us say you have this genome like this, and the reads that you are getting is, so this is approximately 10 mer reads that you are getting, and you see that you are not getting a perfect coverage. So that basically means that you're not having all the 10 mers, okay, that are there in the that are possible in this read, right? Because we are only getting 4 10 mers from this region of the genome. So what you do in this case is you boost the coverage of your k-mers by breaking the read into smaller k-mers. All right. What do I mean by this? So this is what the read that we got was a 10 mer, but what we do is we break this read itself into a 5 mer. Okay. So we break this read into a 5 mer, and by breaking this read itself into a 5 mer, each of these reads, we artificially boost the coverage of k-mers. And now the original idea for constructing the De Bruijn graph is met. That is, that your particular DNA fragment that you would want to construct, the entire k-mer composition is present, right? So when we talk about the 10-mer composition, the entire 10-mer composition is not present here. But when you do this read breaking, you instead of making a graph with a 10-mer, you make a graph with 5-mer, right? uh, when you make a graph with 5-mer, then you see that all the 5-mers are present. So the 5-mer composition of this DNA string is complete. However, the 10-mer composition of this DNA string is not complete, right? Because there is improper coverage of of this particular DNA region. Is this clear? How we solve this problem? So we
Yes,
artificially
sir.
break the reads. Yeah,
Yes,
Yes,
it's
that's
clear.
correct.
yeah. All right. So, how do we deal with this essentially? So, when you want to make De Bruijn graphs from reads, in reality, how are we dealing with it? You have DNA fragments of length L, right? In the from the sequencing machine. This L is typically much larger than K, not much larger, but larger than K. You construct graphs that might have too many nodes, right? Because since L is large, so because you have large reads, so you'll have many more possible Elmers here. So one thing that you do is to reduce the size and to boost the coverage, you break the L into smaller k-mers. All right. So what you do is you break the read of length L into a smaller De Bruijn graph for that individual read, right? Now what you do is you will now start to because this is k-mer is k is much smaller than L, so the graph is going to be having much lesser number of nodes itself. And now using the same idea for constructing the De Bruijn graph, you're just going to glue together all the nodes which are similar across all the reads, and you are essentially going to now construct the entire genome. So now if I ask you to combine to basically write a pseudocode to calculate the coverage from reads, I hope you can do it, right? You will have to make De Bruijn graphs twice, one for the read and one for the genome. Everybody is on board, or
So
So just a
could you repeat
question.
this once again?
so earlier here I've asked you to make a pseudocode to calculate genome coverage, right?
Yes, sir.
I am basically starting with k-mers, right? But in
Yes, sir.
reality, you are not going to get a k-mer, you're going to get a read, which is having the length greater than a k-mer. So what you will essentially have to do is you'll have to construct the De Bruijn graph for the read first, right? The DNA fragment which comes out of the sequencer. And then you are going to use this De Bruijn graph to make the De Bruijn graph for the entire genome where the reads come from. And then you can
Okay, sir.
calculate the
Got it.
coverage. Okay, so there is also, however, a problem if you have small values of K, the coverage is going to be high, but it's also going to mean that you're going to have more repeats, right? Because just by chance, a smaller K would give you more repeats. Okay, so the next problem is the problem of, I mean, even without read breaking, the problem is that sometimes you will always have gaps in the coverage. So when you look at the genome here, so there are some locations, you see there are gaps here. This even read breaking is not going to even solve this problem because you don't have any reads from these regions. So in order to solve this, the softwares whichever whichever are being used right now, they essentially try to infer contigs, okay, a small number of contigs rather than the entire genome itself. So the contig is nothing but a contiguous genome segment, a contiguous genome segment which uh, is having good coverage. Okay, so do you think we can find contigs using a De Bruijn graph? Any ideas around this? Let's try. So when you talk about contigs in a De Bruijn graph, you have to define a contig. A contig is a path in a graph which is non-branching. Okay, so the in degree and out degree is 1 for each intermediate node. Then you are going to have a contiguous genome segment that is going to be represented in every assembly. Okay, a maximal non-branching path is a non-branching path that cannot be made longer in any other direction. If you make it longer in any other direction, then the in degree and out degree of some of the nodes is going to be more than 1. Okay, so maximal here is means locally maximal, not globally maximal. So how do we do this? Let's take one of the original example that we were working with. And in this case, what you do is you make sure you get only those nodes which have in degree out degree as 1. So for example, when we take this, in degree out degree is all 1. We take this path, in degree out degree is all 1. And then we break these things into smaller. Right? So what does this mean? This essentially means that every assembly, all these subpaths will be present in any assembly, whether you are doing a right assembly or wrong. I mean, any sort of algorithm you use, these paths should always be present. All right. And when you essentially complete these paths, what you are essentially getting are contigs. So contigs are nothing but non-maximal branching paths of the genome assembly. And in order to now confirm whether this particular contigs are how they are joined together, what you can essentially do is you can design primers which span two different contigs, right? And you can then PCR out, and then you can specifically sequence the fragment in between. And once you know that this fragment is actually joined, then you can actually connect these contigs and you can make what's called super contigs. Okay, so what's the other problem that we are solving? The other problem is the reads are sometimes error prone. Now, when you say reads are erroneous, this essentially would mean that one of the bases, let's say, is called incorrectly. So instead of, let's say here you have a TAT, instead of a TAT, there's a TAC here. So this T is incorrectly base called. So when you are from the Illumina machine, when you're reading the spot, maybe the two spots are coming close to each other, or the fluorescence is not working as expected. So you get the wrong fluorescence. So you call it instead of a T, you call it a C, right? In one of the clusters, and you essentially get a wrong read, right? Incorrect read. So if you try to make the De Bruijn graph of these two reads now, how will they look like? Any ideas? If you have both these reads present and you make a De Bruijn graph of these reads, so L equal to 10 here, and now you make a De Bruijn graph with K equal to 5, what will you see? So what you see is a bubble. So let us say you have this read like this, right? And as soon as you find the read fragment corresponding or k-mer corresponding to the error, it sort of branches out like this. Okay, is this clear to everyone?
Yes, sir.
Yes, sir.
Yeah. So now what happens is, if because these errors are not going to be as frequent as the correct sequence. Okay. So in a typical De Bruyne graph, what you would be having is you would be having weights of these edges. So the number of times you will see this particular fragment, remember, we are doing PCR, right? After the DNA fragmentation step in sequencing. So it is not likely, but it is 100% you will be seeing that the same fragment is going to be sequenced multiple times. So when the same fragment is going to be sequenced multiple times, you are going to be seeing that the correct path is going to have more k-mers. Okay. There are going to be more nodes on the correct path, more number of times you're going to have these edges in the correct path than the incorrect path. So in a proper De Bruyne graph, you are going to have multiplicities being shown. So if you have the incorrect read, say only one time, you are going to only have a single, like a bubble with a single weight like this, right? And if you are having the correct in the correct path, you're going to have more number of edges, more number of k-mers overlapping, more reads representing the correct path. Okay. So what you do then is once you make the De Bruyne graph, whenever you see a bubble which is having less number of reads or less number of k-mers supporting it, you just clip off this bubble because this most likely would be representing a read error. Okay. So bubble is basically two disjoint paths connecting the same pair of nodes. And in this case, it will be less than some threshold length. Okay. So if this length is too much, then you can imagine that this probably is not coming from just a read, but it is coming from something which is more relevant, something like what's called an insertion or a deletion in the genome. You don't have to worry about it right now, but typically you talk about these bubbles when the length of the bubble that you are getting is typically smaller than the length of the read that you have. Okay, so essentially what you do is whenever you see that this number of reads supporting a bubble are small, you just remove the bubble. Okay, this can also happen when repeated regions are there in the genome, right? So in the case of repeated regions, what are you going to have? The bubble length is typically going to be much larger than the read length. So in that case, you don't remove the bubble, but you consider it to be it as a inexact repeat. Okay. So lower multiplicity paths are likely errors. When we say lower multiplicity, it essentially means that the coverage, so the edges, the arrows that are going from two nodes, their multiplicity is less. So in the case of errors, this would be, let's say, supported by only one read one read uh, at a time. But like the original path, as I said, the path where you don't have any errors would be repeated by many more fragments. So you will just clip off the paths which have lower multiplicity. Okay. So typically, this is an example of how it looks like. So this is a bacteria, the N meningitis. So after removing bubbles, the small bubbles, you essentially see that there are still some repeat paths in red, and they are paths in red which are sort of repeating, but they are representing what's called repeats rather than sequencing errors. So here you see that a lot of these paths actually have this kind of hairs coming out, right? So just these orphan nodes which are just sticking out. Can you tell me what this could be? What could these be representing? So these are also errors, these things which are sticking out. Any ideas what these could be? What kind of errors could these be? Okay. So tomorrow in the class we
Deletion errors?
discuss. Say that again.
Sir, deletion errors maybe?
Deletion errors. Okay. Why do you think these are deletion errors?
I mean, it's like just the node